So let's move on and look at the values that Watson did correctly, I would say, look at. So here I've plotted the proportion of the towers, which is maximally stable, so the number of towers with weight 0 with n bricks divided by 3 to the n minus 1. And I've done this all the way between 1 and 250 in the knowledge that in fact there's something fishy going on in the beginning. So I mean, these values out here, for instance, there's one that's repeated between 3 and 4. This is somehow some initial behavior which probably is not going to be important at the end. And so since we already have the suspicion that this is going to follow some power law, then I will make a doubly logarithmic plot. And so this is what I've done here. I simply put in ln here and here. And in order to get a feeling for how this behaves, I press the 1 equals the 1 colon 1 button up here. That is sort of a constrained scaling, so that means it uses the same axis here and here, so that when you look at the slope, this is actually meaningful, because otherwise Maple will rescale so that it becomes a square when it does this kind of plot. And so you can see that there's a negative correlation, as you would expect, because these numbers decrease, and also that it looks very systematic when you make this log-log plot. Apart from a bit of noise in the beginning, it looks extremely systematic and looks like it has a negative slope, which is somewhere between 1 and 2. So I will do a fit, and this is the same as before. I just pull out the 2 coordinates and ask Maple for the best line through it. And when you then retransform by taking, because this was a fit to the log-log, so in order to come back to the original, the approximation of the original numbers, this would be taking the exponential of the fit of the logarithm like this. And so this is what we get out. And actually maybe I should just put in, if we just take this, I'll call it T-fit, so for transformed fit, I will unapply this equation or this expression with x. And now I think it's probably always a good idea to compare the transformed values to the transformed values. So I'll take this plot here and plot it next to my my untransformed fit. So I'll use display and display, and I will plot T-fit of x for x from 1 to m next to this plot that I already did. And as you can see, it sort of fits very nicely. Of course, perhaps a little bit hard to see because all the action takes place down in the low values. So I can use, I think I can go y equals 0 to 0, 1. Nope, maybe that's view. Like so. Okay, so I've cut out the high portion, and you can see it sort of seems to fit very nicely, even if I zoom in a lot further, and something like this. Right. So this is a quite convincing fit, and of course you have to wonder about these constants that we encounter up here, and I think that we'll return to the constant term up in the numerator, but I'm going to make the qualified guess that in fact the number we're seeing here, the power of x, is not this number here, it's simply 1.5. And I'm doing this a little bit because of some insight that I have from these kinds of questions, that there is a tendency that when you're studying problems that have this kind of spatial behavior, that these powers of 1.5, I mean, it's actually -1.5, they tend to occur very often in these kinds of problems. So this is the end of that. So this is the now this is also, I've plotted the observations together with the fit in the log-log picture. Still very good fit. But I think that's about all that I can say about this. Now let's try to go on a little bit further and see if we can come up with a better understanding of what happens here by looking not just at the case where the weight is 0, but also looking at other weights. So I'm going to take a matrix where I've taken the observations, and I want to put them in a matrix so that you can see the behavior that comes up when you compare various numbers of bricks and various choices of weights. The thing is, though, that we run into this problem that we've had before, that this matrix is too big, that Maple wants to show it to me. That's simply because I sort of said, well, the maximal weight will be something like the square of the number of bricks, and putting this into a matrix, I get something which is bigger than what Maple will allow me to show. So we can fix this by changing the interface, putting the R table size to infinity. So that means that Maple will try to print a matrix no matter how big it is. The thing, of course, is that then, I mean, I can't say I wasn't warned, but this is going to be not so pretty. I'm going to make it slightly smaller. Maybe you can sort of see the pattern. So what happens here is that, of course, if there's only one brick, then the number, I mean, so I'm taking the proportion that fits the various kinds of weights. If there's only one brick, then 100% of them will end up in the 0 weight. If there's 2, then we have 3 choices equally common. If there's 3, then we have like 1, 1, 2, 1, 2, 1, 1. It's actually less doable to get the weight to be 0. This probably explains some of the weird behavior we saw in the beginning. And then when you sort of keep on going, you see that there's a tendency that the numbers are big in the middle, as you would expect, and tapering off at the sides. I could try to show you this in a plot. So what I've done here is I'm using something called a matrix plot, which is often quite useful. So if you have data in a matrix, you can ask Maple to make a plot of it in a sort of histogram type of setting. And this is what I've done. So you see, you know, at the very beginning, I have just a 1, then I have a third, a third, a third, and so on. But when you get down here, of course, this is a little bit small, perhaps, but already at 7, you don't have to have been brainwashed a lot by probabilists to see that this looks a lot like a normal distribution. So what we have here is something that looks like a bell curve, and this is sort of an inspiration for another thing that we can try to do. So that's what I'm going to try to do now, is I'm going to say, okay, let's consider this data as though it was something that we encountered in a real-life science experiment. Then I think it's very likely that we would deal with this kind of data by saying, okay, here's a normal distribution. What is the variance of this normal distribution? So I'm throwing the sort of standard descriptive statistics toolbox at this data, and this is built into Maple. So I'm asking Maple to compute the variance of the observations. This has a weird syntax. Let me make this big again. But I'm sort of, it's the same kind of idea. You know, I look at the observations and I have the weights. That's the number of observations at each entry. So this is not a tuple of observations. It's a list of frequencies of the various observations, and of course Maple can deal with this. I mean, we could also do it by hand, but this is built in. So that's what I'm doing here. And now I'm asking Maple to compute the variance of the observations. And this takes a little while. While we're waiting for it, let me point out that I put this inside a procedure with a remember option. And this is sort of me being lazy rather than clever, because the point is that I want to use these numbers again and again. And in order to not have to sit and wait like we're doing now, I'm putting it inside a remember option so that the data is stored there, so we can just pull it out when we need it again. So this is going to take quite a long time to do this first plot, but when we've done this, then next time the data is already stored in the remember table of getVar, and so we don't have to wait for that again. So I mean, this is not a remember option that I'm using because I want to use this in a recursive way or anything like this. This is just a quick and easy way of saving time the next time I want to look at these observations. Okay, so this is the variance that I got out from looking at my numbers up to 250. So remember, this is quite a lot of data. It looks quite systematic, right? So what does it look like? It looks like a parabola. So I'm aiming for a power law. So I'm aiming for some sort of log plot. And this is what it looks like. And it looks, convincing that the behavior that we're seeing here is following some power law.